Hello everyone and welcome to another video. Today I'd like to talk about one of the most famous power series in mathematics, namely the Taylor series. So our game plan for today is I want to talk about what a Taylor series is, as well as derive how we obtain the Taylor coefficients for this series. Then we're going to look at a couple of examples of Taylor and a more specific version of that, namely the Maclaurin series. And then we will take a gander at how we can use this Taylor series to possibly evaluate integrals in a kind of approximate fashion. And then the last thing we're going to talk about is extending the idea of Taylor series, which we're going to start with in one dimension. We're going to extend this now to multiple dimensions, or talking about Taylor series of multiple variables. And that's going to lay a lot of the groundwork for some of our future discussions on things like numerical optimization and linearization in a couple of other different mathematical domains. So if that sounds like fun, why don't we go ahead and get started. So the Taylor series, the idea with the Taylor series is that it's a special type of power series, right? And remember, again, the idea with a power series is we want to be able to take some function, let's call it f of x, and we want to be able to represent it as a series like such, right? So this, you can see, this is a series with a bunch of coefficients written around some point A, and the power of these kind of increases with every single term, right? And what's unknown about this power series is we're looking for the coefficients, namely C0, C1, C2, C3, C yada yada yada, all the way up to C infinity, that is going to make the left-hand side equal to the right-hand side, right? So again, the power series, this is just a generic definition of the power of a power series, right? And again, the power series usually goes off to infinity, right? So the rough idea is, again, what makes this powerful, I guess I'm using the word powerful and power quite a lot, but what makes this useful is the fact that we're taking a function, right? Usually any function, and in most cases what we're going to be interested in are continuous differentiable functions, but I guess that's getting beyond the point. We want to be able to take a function and represent it using a simpler form. Of course, the trade-off here is the thing on the right-hand side, it's an infinite series. Each of these terms might be simpler than the generic form on the left-hand side, but you got to take an infinite number of these, and that's what makes it useful or not, depending on your application. This should hopefully be ringing a bell in your head. If you recall, in our previous video, we also discussed a Fourier series, right? And the idea with the Fourier series was, again, we were trying to represent a function f of x, but we were trying to use cosine and sine terms in the Fourier series. Now, with the power series here, we are looking to write it in this form where I don't see any trigonometry, all right? I don't see any cosine or sines. All I see are the independent variable x, and then these coefficients C0, C1, C2, and then this term A. So A here is sometimes referred to as the expansion point, and I think it's going to be very clear in a couple of minutes why this term is called the expansion point of the power series. And again, the thing that makes this a power series is that the term of the difference between the independent variable and how far it moves away from the expansion point, that's raised to the 1 power, the 2 power, the 3 power, the 4 power, all the way up to the infinitieth power, right? Okay, so the first thing we need to ask ourselves is we want to look for a very specific set of coefficients for our Taylor series. So again, the Taylor series is if we use a very specific way to calculate C0, C1, C2, C3 for this power series, okay? So let's quickly talk about the derivation of these coefficients. So the derivation of coefficients. Right, so again, the goal here is I want to find these terms C0, C1, C2, yada, 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 right? All the way up to here. Theoretically up to infinity, right? Okay, so the first thing we should note is take a look at the definition of this power series. What's interesting is if I evaluate the function f at x is equal to a, right? Okay, so if I do that, if I plug in x is equal to a here, notice this term becomes 0, this becomes 0, this becomes 0. All of the terms above C0 become 0. In fact, this just turns into this. Isn't that really interesting? right? So at x is equal to the expansion point, you just have this C0 coefficient. So actually, this tells us what the C0 coefficient is, right? The C0 coefficient, it's just the function evaluated at the expansion point, right? So great, box this up. This is one of the coefficients we needed, right? Didn't we say we're looking for C0? Got it, right? All you do is evaluate the function at the expansion point. Okay, let's take another look here. Let's come back again to the power series, and let's go ahead and take a derivative. And maybe, tell you what, let's label this so I don't have to keep referring to it as this. Let's call this thing equation 1, right? So take derivative of equation 1 with respect to x, right? So I'm going to write this like such. How about f prime of x? Right? So this is the first derivative with respect to, I guess there's only one independent variable, it's x, right? So it's just the derivative of x the derivative of f with respect to x, right? So, all right, what is that? Well, let's take the derivative of the right-hand side. So if I take the derivative of the right-hand side of this, notice here that this becomes what? That C0 goes away. This here becomes C1. Right, wouldn't you agree? Plus, this becomes what? 2 times C2 x minus a plus 3 times x minus a squared plus dot, 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 right? Off to infinity. Would everyone agree that's what we get? Okay. Now, what's interesting is, let's call this maybe equation 2. Okay, let's go ahead and look at what does equation 2 look like at x equals a again. So in other words, I'm looking for f prime at x is equal to a. I'm looking for this, right? So again, you look at this expression, and when x is equal to a, what? This becomes 0, right? This becomes 0. Everything else above C1 becomes 0, right? Would everyone agree? So this becomes C1, right? Perfect. Look at that. That's the other coefficient we're looking for. We're looking for C1. So box this up. We went ahead and found this, right? Okay, let's keep going. Let's now, let's take the derivative of equation 2 with respect to x again. So, shucks, running out, didn't manage the board very well here, but let's do this here. So take derivative of equation 2 with respect to x, right? So that is f prime prime, right, of x. So I take the derivative of this. Okay, so now I knock out the C1. This becomes what? This is 2 times C2x. Oh, no, sorry. Nope, the x minus a is gone, right? This plus this here. So I'm going to write this as this. This is going to be 2 times 3 times x minus a. Would everyone agree? All right? And then plus all of these extra terms, right? Higher order terms, right? And I guess maybe we should have written a few of these out just for giggles so we could see the pattern. I'm kind of debating if I want to do that. Sure, tell you what, let's come back up here. What would this term have been? This would have been a 4 times x minus a cubed, right? Plus da 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 da. Okay, so then when I take its derivative, this is actually going to be what? It's going to be 3 times 4 times x minus a squared, right? Plus dot dot dot, like that, right? And actually, yeah, okay, I think we'll get the pattern here in a second. Okay, so again, now let's go ahead and evaluate this f prime prime, right, at a. Right? So again, what's great about this is notice that this is going to knock out this term here and this term and everything else. So again, everything above this thing 2 times C2 is going to be 0. So this is what ends up happening. Now, again, you could solve this at this point, but tell you what, let's leave this like this for a second. Okay? You basically found C2, okay? Let's do it for one more iteration, then I think you're going to see what the pattern becomes, okay? So let's go ahead again. We'll label this here. This is now equation 3, right? So again, we're going to take the same thing. So take derive of equation 3 with respect to x, right? So now I'm looking at f prime 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 of x, right? So I got to take the derivative of this thing here. So again, this gets knocked out. This becomes 2 times 3, right? This is 2. Oh, shucks. What did I do? I dropped, sorry everyone, I dropped, oh boy, where did I missed, crud. Sorry, there was a C3 here. And a C4, yikes. Okay, so that should have shown up here. Sorry, there should have been a C3 here. And there should have been a C4 here. Okay, there we go. Okay, that looks better. Okay, so this becomes 2 times 3 times C3, right? Okay, plus this now becomes 2 times 3 times 4 times C4 x minus a, right? Plus all these other terms. And again, this pattern would have, this factorial type pattern would have kept continuing on, right, with higher powers. So now, again, we do the exact same trick. So now, what is the f prime 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 at a? What does that look like? So again, that knocks out this term here, because this difference becomes 0. Everything up here becomes 0, so we end up with 2 times 3 times C3, right? So does everyone see the pattern at this point? So what's interesting about this is if you keep going, what we end up seeing is that the pattern is that if you take the nth derivative, so again, this here of a, right? This is shorthand notation for df dx, right, to the nth power. And then I'm going to evaluate this thing at a, right? That's the same notation, right? That's the notation we're using here with all of the primes. Sometimes you're just going to see it here as a superscript, but in parentheses. So again, this is not a power, right? This is actually the nth derivative of f with respect to x evaluated at the point a, right? That's what all this means, okay? But the pattern you end up seeing, right, is that what we have is this actually ends up being n factorial times c to the n, right? Because does everyone see that's the pattern that evolved out of this? Okay, so this coefficient that we're looking for, c to the n, whatever one we're looking for, right? This is for n equals 1, 2, 3, all the way up to infinity, right? Okay, so just solve this. So all we end up here with is the coefficient c to the n. It's just the nth derivative of the function evaluated at a, right, all over n factorial. So this is what we were going after, okay? So this gets us all these coefficients, C0, C1, C2, C3, C4, again, all the way up to C infinity, right? We've got the expression for it right here. It's just take the function, take its derivative n times, evaluate that derivative at a, and then divide through by n factorial, right? Okay, so that's perfect. Let's now go ahead and substitute that into our expression for our power series, right? We choose these coefficients in our power series, we end up with basically what's known as the Taylor series. So tell you what, give me a second to erase some of the board, and then we will substitute this in and just write it out for completeness. All right, so I've just rewritten our power series, which now becomes a Taylor series because we are choosing a very specific set of coefficients C0, which you can see here. Here's our C0, here's our coefficient C1, here's our coefficient C2, here's our coefficient C3, etc., on to infinity. But this now, because we've chosen this specific set of coefficients for our power series, this is what's known as a Taylor series, right? So the more compact way that you'll usually see this written, right, is I think we all see the pattern at this point, is the Taylor series says that this f of x, right, is given by, if you look at this thing long enough, it's basically just the sum from n equals 0, whoops, that's a funny looking 0, to infinity, right, of the coefficient here is, again, here, we've got it right here. It's f to the n, evaluated at point A, all over n factorial, right, times x minus a, would being our expansion point again, to the nth power, right? So this, if we box this up, this is our Taylor series, right? right? And again, it's an infinite series, but again, at least it does show us how to calculate each term of this series explicitly. Now, obviously, sometimes an infinite series, while it's mathematically correct, it's not the most useful thing in the world. I don't know about you, but I'm not eager to write out an infinite number of these terms or try to implement this in a MATLAB or a computer simulation environment, carrying out going from n equals 0 to infinity. So sometimes what might be a little bit easier is to just approximate this with what's sometimes referred to as a partial sum. I'm going to denote this here as Sn of x. So the partial sum is basically taking this exact same expression, right? Our Taylor series. But instead of going from n equals 0 to infinity, just go to some number. I'm going to call it big N, right? Capital N. You can clearly see here that this is not taking all the terms, right? We are going only up to capital N terms. So that's what I'm going to call as the partial sum. So this thing over here is sometimes referred to as a partial sum. And again, it's hopefully the name makes sense is because I stopped. I didn't take all of the terms. I just went up to big N. So that's why I have to write an approximate sign here. So this here is tractable, right? You could take maybe, 1, 2, 3, 4, 10 terms. Maybe 20 terms is fine if you've got a numerical package that's calculating all of these terms for you. But again, my goal here is I don't want to go all the way up to infinity. I'm going to just stop here at big N, right? Okay, so let's talk about something. While we've got the expression written up here, remember we talked about the Maclaurin series as well at the beginning. So the Maclaurin series, I think it's actually very easy to see what's going on because we've written it out in such a literal black and white fashion. So Maclaurin series, AU, I always spell this wrong, C-L-A-U-R-A-N. Okay, Maclaurin series. It's nothing more. It's basically, it is a Taylor series with a equals 0, right? With an expansion point of a is equal to 0. So literally, again, this expansion point a is somewhat arbitrary in the sense that you kind of get to pick it depending on your application. Well, one thing you might want to pick is just pick a is equal to 0. So that's all it is for a Maclaurin series. It's really, really simple. So, we could just write it out here. So f of x, if you want to write f of x using, instead of a Taylor series, write this as a Maclaurin series, it's the exact same thing where I'm going to sum from n equals 0 to infinity, but it is just going to be everywhere you see an a, just put in 0. So here's your coefficients for the power series, and then it's just x to the n, right? Okay. So, all right, we've written it out. I think we have a rough idea of what they look like. So tell you what, let's go ahead and look at an example. So give me a second, I'll erase the board and we'll write up 2 examples. We'll look at one example of a Taylor series, one example of a Maclaurin series. They're really basically the same thing, but I think it'll help get us some practice. All right, so let's look at 2 very simple examples. Both of these are going to be looking at trying to find the power series representation of e to the x. So the first one I want to look at is the Maclaurin series of the function e to the x, and then let's look at the Taylor series of this exact same function, but at an expansion point of a is equal to 2, okay? So let's go ahead and start with the first one, since the Maclaurin series is probably the more simple situation to go with, right? So as a quick note, we saw earlier that we're going to need the derivative of this function at the first derivative, the second derivative, the third derivative, yada, yada, yada. One thing that's really nice about this function, right, is that the nth derivative, right, this is just e to the x, right, for all n, right? Doesn't matter if I take for I guess all n in the integers. Right, if I take the first derivative, second derivative, third derivative, fourth derivative, fifth derivative, the infinite derivative, it's still e to the x, right? So that's going to make our life a little bit easier in some of these cases. So let's look at first the Maclaurin series. So let's get the Maclaurin series. Right, so that said that f of x, like we said, this is just going to be f to the n at 0 all over n factorial x to the n, all right? So let's just write out a couple of these terms. So let's write out the n equals 0 term. Oh, whoops, sorry, there should have been a big sum here. Sum equals 0 to infinity, right? So this is basically f at 0, right? That's the n equals 1 term, the n equals 0 term. Now the n equals 1 term is f prime at 0 all over 1 factorial. That's a coefficient. And then I have just x, right? Okay, then plus f prime prime at 0 all over 2 factorial x squared, right? And then finally f prime 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 0 all over 3 factorial x cubed plus yada 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 all the way out to infinity. So, okay, let's go ahead and write this out. So f at 0, that's just the function evaluated at x equals 0. So this is just e to the 0, right? Okay, plus the first derivative of f, again, which we said is just still e to the x. So this is still just e to the 0 all over 1 factorial, right? Times x, right? Plus, then here we go. This is still e to the 0, right? All over 2 factorial x squared plus e to the 0 over 3 factorial x cubed plus yada yada yada, etc., etc. So again, long story short, this thing just boils down to sum from n equals 0 to infinity of basically at e to the 0, right? These are all 1s, right? So this thing could all be written as just x to the n all over n factorial, right? So here's the Maclaurin series representation of this function, right? Okay. That's pretty great. Now let's do the exact same for the Taylor series, right? So 2. Let's go ahead and get the Taylor series. So again, just writing this out, so we said the Taylor series of this thing was, again, sum from n equals 0 to infinity of f to the nth derivative, right? Evaluated at the expansion point a all over n factorial times x minus a to the nth power, right? That's what this looked like. So again, let's write out a couple of terms. So let's write out the n equals 0 term. So that is actually the function, its 0th derivative, so that's just itself, at the point A, right? This is the n equals 0. Now, plus, let's go ahead and get the n equals 1 term. So this is f prime evaluated at a all over 1 factorial times x minus a. Right? Now the n equals 2 term, that's f prime prime at a all over 2 factorial x minus a squared, plus etc., 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 right? Okay, so again, substituting in all of these values, so the function evaluated at a, it's just e to the a, right? So this is e to the a, right? Plus, this guy right here, again, this is also e to the a all over 1 factorial times x minus a, right? Plus f prime prime at a, again, the nice thing about our function f is its derivative is still just itself. So this f prime prime of a is just still e to the a all over 2 factorial x minus a squared plus yada yada. Keep this thing up for as many terms as you would like. Okay, so now I guess what we could do is we could plug in, we know what our expansion point a is, right? So we can say, note, we know that a is equal to 2. Right? That was the expansion point that I'm interested in, okay? So now, let's go ahead. This just becomes e to the 2, right? Plus e to the 2 all over 2 factorial x minus 2, right? Plus e to the 2 all over 2 factorial x minus 2 squared plus etc., 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 right? So again, you write this thing out long enough and you can write this, you see the pattern, this is n equals 0 to infinity, right, of e to the 2 all over n factorial times x minus 2 to the nth power, right? So this is the Taylor series approximation. Or I guess, again, this is not approximation because we're going up to infinity actually in both of these, right? This is the Maclaurin representation of the function, and this is the Taylor series representation of the function at the expansion point of a is equal to 2, okay? So what might be helpful now to gain some insight into what these functions look like and how they behave the way they do and why some of these things are called things like the expansion point and things like that is, tell you what, let's jump over to Mathematica where we can actually plot three things. So we're going to plot the original function, right? This is the thing that we're starting with, right? We want to plot that. Then what I want to do is I want to plot this thing. In fact, and I'm not going to go all the way up to infinity. I'm going to take a partial sum. Let's go just maybe 1, 2, 3, 4 terms. We'll see as you increase the number of terms in this this representation of the Maclaurin series, what does it look like, right? So that's the second thing we're going to plot. That, and then same thing over here. Let's also plot this Taylor series representation. Again, not going all the way up to infinite terms. Let's stop at a certain number and just see what it looks like. So, all right, let's jump over to Mathematica and see what these three functions, how they behave. All right, so here we are. So the first thing we should do is define the original function, right? So that was f of x is e to the x, right? Oops, e to the x, okay? So that was the original function, and now let's go ahead and define the partial sum approximations. So in other words, I'm going to look at, how about make something called f Maclaurin of x, and also we're not going to go up to infinity. We're going to go from n equals 0 up to like some number. Let's call it capital P. I actually can't use the capital N like I was using in the whiteboard, just because capital N is already reserved in Mathematica. So I'm just going to use capital P as the total number, the upper limit of the number of terms that we want to go to in our sum. So again, let's go ahead and define this simple function. And as we said on the board, this is basically the sum of the terms. It was what? It was x to the p all over p factorial, and we are going to go from p equals 0 up to capital P, right? Okay, so that was the Maclaurin series, and again, that is a partial sum going from 0, 1, 2, all the way up to capital P number of terms, right? And then let's do the same thing for Taylor. So f Taylor is also going to be a very similar format. It's just a different sum, right? It's just a different power series. So this was sum of, I think it was e to the 2 all over n factorial, or I guess in this case I'm using p. So p factorial, and again, p goes from 0 up to capital P. Okay, so there we go. Those are the these are all of our definitions. So for example, we can just show, you know, what does let's look at these. What do these partial sums look like, right? So, for example, f Maclaurin, how about let's say of x, and let's take, how about 3 terms? And then same thing, let's look at f Taylor, 3 terms of this thing. So if you look at this, let me see here, that's actually interesting. Oh no, sorry, haha, I totally messed this up. Here in the Taylor series expansion, I completely forgot the other term, which was the x minus the minus the expansion point, right? All the way to the power p. Whoops. Okay, so sorry. There we go. That's the actual proper Taylor series expansion. So now when we look at this, let's see. There we go. This looks a little bit better, right? So here's the p equals 0, 1, 2, 3 term of the partial sum of the Maclaurin, and then similarly here's the p equals 0, 1, 2, 3 term for the Taylor series expansion, right? Okay, so now what we should do is let's go ahead and plot these, right? So let's plot these functions slash approximations, right? So let's just look at, how about plotting, let's plot the original function. Let's go from x is some x minimum to some x maximum, and tell you what, let's go ahead and define what those x minimum is. How about let's go from -1 to how about 3? Something like this, okay? So again, here's the original function, right? It's just this exponential here, right? It's e to the x, and as everyone knows, this is what e to the x looks like, right? It blows up, okay? So let's also, how about plot the Maclaurin series representation, right? And let's go from, again, we'll pick some maximum number. Let's say, how about p max let's do 3. 3 terms to start, just like we did up top. So we're literally going to be trying to plot this function here, okay? So let's do this for like such, okay? And we'll go from the same range, x min to x max, something like this. And you know what we should do? Let's make this a different color. Let's make this plot style, how about red? Okay. So down below, here is the Maclaurin series approximation of that function, and you can see they look pretty darn close. In fact, you know what we should maybe do? Let's put the 2 of them on top of each other so we can see them both at the same time. So I'm going to wrap all of these in a show command. And again, maybe let me explicitly, I'll make this one blue, just so we can see the differences. So there you go. Now look at this. See? Isn't this pretty cool? So with just 3 terms in the approximation, the Maclaurin series partial sum, the red line, looks like a reasonable approximation to the actual function f, which was the blue line. And you know what we can do? Let's also throw on the Taylor series approximation, right? So let's also do f Taylor, and we'll take 3 terms, and we'll again go from x min to x max, and for giggles, let's make this one, how about green? Oops, green, like that. Okay, and look at that. So the green line is also pretty reasonable. And what we can do is we can start changing this p max number, and we can try to understand how do these approximations or these partial sums, how do those change as we change how many terms we're actually taking in our expression. So maybe instead of p max equals 3, let's drop it down a level to 2. And look at that. It gets a little bit worse. In fact, instead of me manually changing this p-value, tell you what, let me manipulate this. Let me wrap this whole thing in a manipulate command. And we are actually going to manipulate the value of p max. Let's make this thing run from, how about 0 to, I don't know, 7, and go in increments of 1. Something like this, right? Okay, so I think it's like that. Oh, crud, I missed a comma or something. Hold on. Shoot, oh, sorry, I put the p, this is in the wrong thing. This is inside the show command. I don't want this inside the show. I want this out here. There we go. There we go. Okay. And I guess we can get rid of this out here. Let me just clear p max. Okay, so we'll clear p max. We don't know what it is. Okay, so now, yeah, this should work here. And actually, you know what we should do? Let's actually also add a title to this. So to do this, let me put some plot options here. So what we can do is let's go ahead and add a plot label. And what we're going to do is I want to write how many terms are we taking in our expression. So I'm going to say this is with p equals, what is this, p max is what I'm using. Like this. Okay. Yeah, I think that should work. So, okay, let's shift enter this guy, and there we go. Here we are. So look at this. Let me make this a little bit bigger so we can hopefully, come on, it's not going to let me make this bigger. All right, I can make this bigger another way. Let's we'll expand it like this. Okay, so now I've got this manipulate window, and you can see as the p max value, it's starting here at 0. So this is like the simplest version of the approximation, and we can see if you remember from our Maclaurin and Taylor series definition that when you only take one term, it's just a constant, right? It's literally the function evaluated at the expansion point. So notice this. This is interesting. The Maclaurin series approximation, the red line, right? It nails the function exactly at the expansion point, right? Because we said if you take only 0 terms in that expansion, you get the function evaluated at the expansion point. For a Maclaurin series, that expansion point is 0. So the red line crosses the blue line exactly at x is equal to 0, right? Now, the green line is our Taylor series expansion, and again, we saw that with a Taylor series expansion, if you only have the 0th term in that partial sum, you just return the function evaluated at the expansion point. So again, the Taylor series approximation, it nails the function at the expansion point of x is equal to 2. So everywhere else, though, we see it's a horrible approximation. So instead, what we should do is let's crank up this p max number. So instead of 0, let's look at 1. Now look at this. This is really interesting. If we only take one term in that expansion, now what we end up with is we end up with an affine approximation. Be careful, this is not linear. It looks linear, but a line with like this is actually, it fails the check for linearity because it doesn't go through the origin. So this is actually more appropriately named an affine approximation, right, of the function. So both the red and the green line are basically getting you affine approximations of the function which are tangent to the actual function at the expansion point. Can everybody see that? Can you see it? Right? So again, what's great about this is that the approximation, right, either the red or the green line, it nails the function exactly correctly at the expansion point, and anywhere else, it starts incurring some error. Okay, so let's keep cranking up the number of terms in our partial sum. So instead of 1, let's crank it up to 2. And again, look at this. This is actually, again, fascinating. We are, again, hitting the actual function exactly correctly at the expansion points, and now we're getting better, right? Now instead of a linear or slash affine line approximation, we're getting a quadratic approximation of the function now, right? So it's getting better. Now let's keep cranking it up. So instead of quadratic, let's go to a cubic. Let's go to 3 terms. And look at this. The red line is pretty darn close down here. The green line is pretty close up here. So again, we're starting to converge onto the actual function. So this Taylor and Maclaurin series it's working, right? This power series is working. If I keep increasing this number, look at this. We're getting better and better and better and better. Look at that. Isn't that cool? So you can clearly see as you take more and more terms in this partial sum, the approximation gets better and better and closer to the actual function. Now, let's actually write out what do all of those look like just for giggles, actually. So what I mean is let's make a table here of P max and then F Maclaurin of X and P max. And then let's also look at F Taylor of X and P max. And let's have P max also go from 0 to, I don't know, how about 5 in increments of 1? So something like this. Whoops, and I missed a closed brace over here. There we go. Okay, so here's what this looks like. This is not very easy to look at. Let's put this in a grid format. That way this will look a little bit nicer. There we go. This is looking cleaner. Let's fix this grid a little bit more. Let's put a box around this. How about? There we go. And I'm going to actually zoom out so we can see this a little bit better. There we go. Okay, and actually tell you what, let's also align everything to the left. There we go. Okay, so this first column is the number of terms in your partial sum. So 0, 1, 2, 3, 4, 5. This second column is the Maclaurin series approximation, or that partial sum with the commensurate number of terms. And finally, this last column is the Taylor series expansion about the point of x equals 2. So, again, what's great about this is you can see we get more and more complicated polynomials as we increase the number of terms. But again, you can clearly see from this expression, right, that when x is equal to the expansion point, the approximation, it matches the actual function value at that point. So just to double check that, we can look at what is f at 0, right? This, we should make a little note, right? This should match the Maclaurin series at x equals 0, right? Or I guess technically it should be the other way. It should be the other way around, right? It's the Maclaurin series should match this, right? Because the Maclaurin series is the approximation, right, to the actual value. So there you go. Look at that. The actual function value at expansion point of x equals 0, that's 1, right? And look at this. You can clearly see that anywhere in this column, no matter how many terms you take in this, even if you only have 0 terms in your Maclaurin series expansion, you will nail the actual function value at the expansion point. And similarly, we can look at what is f at 2, right? This should match, or I guess, again, making sure we say that the correct way, the Taylor series with expansion point of a equals 2 should match this, right? So the function value at x equals 2 is e to the 2, right? And actually, look at this. Again, you can clearly see that when x is equal to the expansion point of 2, all of these higher order terms drop out. So again, the Taylor series nails it, right? And that's exactly what we saw up here in this manipulate thing, is that no matter how many terms you take in these approximations, it hits the function exactly about the expansion points, and any more terms that we start increasing just increases the fit around that point, right? So this is working. This is actually a lot of fun, and it's really powerful because we're showing a systematic way that we can generate basically polynomial approximations via this Taylor series expansion about a given expansion point, and have that get closer and closer and closer to matching the actual arbitrary function that we're interested in, right? Okay, so if we're happy with that, let's jump back to the whiteboard and think about this a little more. All right, so we saw that the Taylor series is really good at finding approximations of the function at a given expansion point. Now, before we delve any deeper, I want to circle back a little bit and talk about truncating the series at basically the first term. So in other words, I want to look at taking the sum, the partial sum from n equals 0 and only going up to n equals 1. So what that looks like is this, right? And we saw earlier just now that this is basically an affine function, right? This is an affine function, or an affine approximation of the original function, right? This basically looks like a y equals, you can almost kind of see it, right? Doesn't this sort of look like here's a slope, right? Here's like the mx plus, I guess this together is all like a b, right? This sort of looks like a y equals mx plus b. It looks like a line, but with a non-zero y-intercept, right? So that's why we call this affine. This is not linear, right? It is definitely not linear because of this non-zero offset, right? So a more accurate expression, or the way I like to refer to this, and you may hear this referred to this in other circles as well, is sometimes you'll hear this referred to as the first order approximation. First order approximation. And this becomes very, very helpful when you're doing things like linearizing dynamic systems, or trying to generate numerical algorithms for optimization routines. We may want to look at this first order approximation. I want to just spend a little bit of time though staring at this and making the note, again, I want to really drive the point home that this is a first order approximation, not a linear approximation, right? Because this will fail the linearity test due to this non-zero y-intercept. Basically, it doesn't go through the origin, okay? So what if you want to linearize this system, right? Again, like I said, probably one of the most common places you'll see this. In fact, the way I use the Taylor series a lot is when I'm trying to linearize a system, and people throw around this terminology of linear and then first order, and kind of muddy the water. So I really want to just drive that point home right now. So if we want to use Taylor series to obtain a linear system, right, or a linear function, what you're going to have to actually do is we're going to actually have to define perturbations from this point. So what we're going to have to do is, let's quickly write this down. So to generate a linear function, right, we're going to go ahead and define perturbation. So I want to look at, let's define delta f of x as being f of x minus f at the expansion point, right? So if you think about this long enough, this is almost like a perturbation in the y direction. It's how far away is the function from the function at the perturbation points, right? So this is almost like a delta y term, right? And then we can look at like a delta x term as basically being how far away you are from the expansion point, right? That's this difference. So again, this is like a delta x, right? I mean, in fact, it is kind of delta x, right? So what we can do now is, if with these definitions, let me just rewrite this first order expression, right? So the first order function, right? We said that we have f of x is equal to f of a, right, plus f prime of a all over 1 factorial times x minus a, right? Let me just move this to the other side, right? So couldn't we write this as f of x minus f of a is equal to f prime of a all over 1 factorial times x minus a. Great, now let's go ahead and use our definitions. This term right here, isn't this just what we call the delta f of x, right? And this term right here, this is now delta x, right? So now I could write this whole expression as delta f of x is equal to f prime of a all over 1 factorial times delta x, right? Now, if you look at this term, this looks a lot like y equals mx, right? Something like this. This looks like a line with a 0 y-intercept, so it goes to the origin. So this function right here does satisfy linearity. This is a linear function, right? But again, the idea now is that we are looking at perturbations away from the expansion point, okay? So to drive that home, I think we should probably draw a picture, right? A picture, I think, tells 1,000 words. So let's look at an example here. Let's look at another example. Okay, so I want to look at a function. Let's consider this function. F of x is equal to x minus 2 squared plus 3. Okay? So, if you plot this guy out, in fact, instead of me butchering the plot, why don't I just show a screenshot of what this looks like in Mathematica? So this function, you basically see it's a quadratic, right? Okay, so now let's leave the picture up on that side of the board and let's just keep working this out. So what I'd like to do now is we would like to linearize about some point. Let's go ahead, use a point, I don't know, expansion point of, let's call it x naught here, right? This is the same thing as a, what our terminology was earlier. All I'm saying is I want to pick some x value that I want to linearize about. And again, if you're linearizing systems, a lot of times you'll see terminology of a naught here. It's just an expansion point, right? It's just a Taylor series expansion point. Let's go ahead and pick this value of, how about minus 1? Right? Okay, so let's go ahead, and what we're going to do is step one is let's find the first order approximation of this function, right? Well, that's this right here. We already computed that, okay? So what we can write is that we have f of x is, or I guess technically it's approximately, right? Because we're taking a first order approximation, right? It's just a function at the expansion point plus the derivative, or the partial, right? So I'm going to take the derivative of this with respect to x, right? So it's df dx, right? At the expansion point x naught, right? This times x minus x naught, right? That's the first order approximation. Right? Okay, so let's compute a couple of these things. So how about this term right here? So I need to go ahead and compute f at minus 1. Right? So that's just this function. Everywhere I see an x, you stick in a minus 1, minus 2 squared plus 3. Okay, this is, shoot, I should have done this. Minus 3 squared, 9, 12, right? Isn't this 12? Okay, that's 12, and then I need to compute this term right here. I need to get df dx and then evaluate it at minus 1, okay? So what is df dx? So I gotta take the derivative of that thing, so it's 2x minus 2, something like that, right? And then evaluate this thing at x is equal to minus 1, so it's 2 times minus 1 minus 2, what is this, minus 6? Yeah. Okay, great. So our first order approximation is f of x is approximately 12, right, minus 6x minus, I guess it's plus 1, right? Perfect. Okay, so now what we can do is we could go ahead and plot this. So again, let me overlay this plot, right? This is the first order approximation. Let's overlay it with the original function, right? And again, that's what you see over here. So the orange line is this line, and you can kind of see, as we expect, this looks like a y equals mx plus b. It's basically the tangent line that is going through the function here at the expansion point of minus 1. Right? Now, what's interesting though is we would like to now almost shift the origin of the coordinate system, right? And I want to now start looking at perturbations away from the expansion point. And the expansion point now, I'm almost shifting the coordinate system to the location of, where is it, minus 1 here? And then the y value here is, what is that? Is that 12? Yeah, here, right? 12. So it's almost like I'm moving the coordinate system. So I'll try to illustrate that here. I want to move the coordinate system up to the origin to this location, because I want to measure how far does the approximation vary from this expansion point here, right? So again, before I do that, let's look at the way I've labeled the original axes on the plot, right? Notice the x-axis is labeled as plain old x, and the y-axis is labeled as plain old f of x, right? Now, what we can do is, if I want to now use our formula we calculated over here, right, to get a linear function, right, we can easily do that. Let's come over here. I'll tell you what, let me just erase the middle of this, just so we can keep the picture up on the other side, okay? Okay, so now the linear function is what? It's delta f of x is equal to f prime a all over 1 factorial delta x. And again, we already calculated what this was. This was minus 6, wasn't it? Okay, so this is actually really simple, right? Here is the other function we can think about plotting. The only problem is I can't plot this function on that exact same plot, right? Because the axes are different, right? The x-axis in this case, right? We're not measuring x any longer. We're measuring perturbations from x. So the x-axis has to be delta x. So again, I can't plot it on the exact same figure because our axes are different. And similarly, the y-axis, it's no longer f of x, right? It's delta f of x. So I almost need a completely second plot, and you can see that second plot, it looks a lot like the orange line in the first plot, except it goes through the origin using this coordinate system here, right? So it's again, it's a little bit of a fine nuance that I want to talk about here, but all I'm saying is that the first order approximation is technically not linear. When we're talking about linear system analysis or using Taylor series to generate linear systems, we're really talking about examining perturbations away from a given expansion point here, right? So again, we're really like shifting the coordinate system, or shifting the origin, or shifting your zero or your datum, or where you're measuring deltas from. If we talk about deltas from the perturbation point, then you obtain a perfectly linear mapping. Otherwise, you have an affine mapping, which is not linear, which could make your life a little bit more difficult in some places. So again, the other thing, maybe before we leave this, the thing that's interesting about this is if you stare at this linear mapping, or heck, if you stare at the first order approximation, right, a lot of it comes down to this term right here in blue, right? It's the partial, or it's the derivative of the function at the expansion point, right? That's really what this term is saying, right? So this here is almost like asking, at the expansion point, right, how sensitive is f to changes in x, right? So depending on your expansion point, this is going to change, right? So on that picture over there, right, the blue line is the original function, and you can see the slope changes as a function of x. If you move in different x directions, right, the slope either gets steeper or shallower, or in fact, right, at some locations, the derivative is actually 0, right? So for example, I think if you chose an expansion point, if we redid all of this and now just said an expansion point of choosing, gosh, I don't know where I can have this here. If you choose a is equal to positive 2, right? I think what you'll end up seeing here is by the time you calculate this partial or the derivative of f at positive 2 with respect to x is equal to 0. So this would now become a 0. So it would almost tell you at that location of positive 2, the function has no change with respect to x, right? It's perfectly flat. So again, your first order approximation, your linear approximation of the system, it is going to change depending on where you choose the expansion point because this partial changes, right? Okay, so that's great. Give me a second to erase the board and let's take a look at how else we can use Taylor series. All right, so let's look at an interesting application of the Taylor and Maclaurin series to use it to actually evaluate integrals, potentially difficult integrals. So let's consider this function here. So f of x is e to the minus x squared, right? And what I'd like to do is I'd like to compute the integral of these functions, right? So I'd like to compute the indefinite integral as well as the definite integral between 0 and 1, right? Now, maybe that doesn't look like that bad, right? It's just an integral, but if you try to calculate this, there's actually not a closed form expression for this integral, right? So in fact, here's a screenshot, right? You try this in Mathematica, and it basically returns to you the error function, right? And the way the error function is defined, it's basically, it's almost like defining its definition is the integral of this function. So it's this circular logic in the sense that there really isn't a closed form expression for this integral, right? So it has to be computed numerically. Or another way you could try to compute this, or an approximation of this, is to use the Taylor series, right? So let's go ahead and try that right now. So what we would like to do is basically get let's do a Maclaurin series actually. How about so a Maclaurin series of f of x, right? So as a quick side note, let me just say, recall, this looks really actually fairly similar to what we looked at earlier. If you recall earlier that we said that if you had just e to the x, right? Didn't we say that the Maclaurin series for this thing looked something like n equals 0 to infinity of just x to the n over n factorial, right? I think we just showed that earlier. So now, instead of x, it's just negative x squared. So what we end up with is the Maclaurin series of this thing, of this function, right? This is just going to be sum from n equals 0 to infinity of, now it's not x, it's now negative x squared, right? To the n all over n factorial, right? Would everyone agree with that? Okay. So you could actually rewrite this if you wanted. If you were careful with the negative ones, you could rewrite this thing as sum of n equals 0 to infinity of, basically pull out the negative 1 to the front. Here's an n, and then you get x to the 2n all over n factorial. I think that's the same thing, right? Okay, great. So armed with this, what we can do is let's compute this first integral, right? So let's get the indefinite integral. Okay, so the indefinite integral, right, of f of x, right? That is just going to be the indefinite integral of, here, jam in this approximation, right? This Maclaurin series approximation. So this is just sum from n equals 0 to infinity of that thing, right? Minus 1 to the n, x to the 2n all over n factorial dx. Great. So now let's just write out a couple of these terms. So we end up now with integral. Okay, so this becomes, I think it's 1 and then minus x squared all over 1 factorial plus x to the 4th all over 2 factorial minus x to the 6th all over 3 factorial plus yada, 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 right? I think everyone sees a pattern at this point, right? dx, right? Okay, great. So now to integrate this thing, we can just go ahead and integrate. So what do we end up with? If I integrate this here, you end up with the, what is this? This is just an x, right? X, and then this is minus, minus, and then this is what, x to the third all over 1 factorial, but then a 3 pops out over here, right? Yeah, I think so. Okay, then this one becomes what? X to the 5th all over 2 factorial, but then I got to multiply by a 5, something like that, right? And then minus x to the 7th all over 3 factorial, and then I think a 7 shows up here, right? Plus yada, 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 and then plus some constant of integration, right? Because it's an indefinite integral, right? Okay, so there you go. So here is an expression for the indefinite integral. And again, I don't know if we we made a ton of progress, right? We said earlier that this indefinite integral of this thing, it was this error function, right? It was this non-closed form expression. And same thing, we traded a function or an integral which does not have a closed form expression for an integral that does have a closed form expression, but it's a infinite series, right? So I don't know, maybe this is, there's some benefits, some negatives, right? Now, where we actually start getting some benefit though is, what if we wanted to do the definite integral from 0 to 1, right? So let me just change this. I just want now the definite integral of this between 0 and 1. So this is between 0, 1, 0, 1, 0, and 1. So all we have to do now, right, is I got to take this thing and evaluate this between, let me erase the box because I guess we got a little bit more work to do now. Okay. Okay, so this whole thing, right, evaluated between 0 and 1, right? So this is going to be nice. It's going to knock out the constant of integration. So we end up with, and all these zeros, right, are going to knock out a whole bunch of this other junk. So we end up with this whole thing. This is now just going to be, let's do the 1, evaluated it at 1. So I need to take this entire expression, everywhere I see an x, I need to evaluate this at 1, right? So this is now 1 minus 1 cubed all over 3 times 1 factorial plus 1 to the 5th over 5 times 2 factorial minus 1 to the 7th all over 7 times 3 factorial, right? Plus yada, 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 right? This is the 1 term. And now I need to subtract off this entire thing evaluated at 0. So it's 0 minus 0 to the 3rd all over 3 times 1 factorial plus 0 to the 5th all over 5 times 2 factorial minus 0 to the 7th all over 7 times 3 factorial plus yada, yada, yada. Oh, and I guess I forgot that constant of integration, right? But this is why it's nice, because the minus sign, the constant of integration will cancel the constant of integration. All this junk here is just a big fat 0, right? So we're just left with these terms right here. And what you can see is, as you keep adding terms, we actually add smaller and smaller and smaller amounts, right? Because this factorial grows, right? So subsequent terms contribute less and less and less and less. So just like we saw in the partial sum case, maybe I can get away with only carrying around, 3 or 4 or 5 of these terms and get a pretty reasonable approximation to this integral. So in fact, let's do that. Let's carry out, let me see, 1, 2, 3, 4, 5. So in my notes, I carried out 5 terms. So let's carry this to 5 terms. So let's do this again. So we have the integral of 0 to 1 of f of x dx, right? This is the thing we're trying to get. So 5 terms of this, I think you get 1 minus a 3rd plus a 10th minus 1/42 plus 1 over 216, right? And then again, you can keep going if you want, but you just add all these numbers up and you end up with what? 0.747487, right? And again, now I guess we got to make this an approximate sign, right? Because we dropped some terms, so we're not exactly there, right? Okay, so this here is our approximation of the definite integral. right? And we can compare that with a much more precise numerical result using the error function. And I think if you do that, in fact, I'll flash up the Mathematica screenshot, and you can see that this number we calculated is pretty darn close to that other number, right? So you can imagine that this is actually a fairly reasonable way to calculate, to numerically calculate integrals of potentially complicated functions if you can rewrite it as a simpler form using this Taylor series or the Maclaurin series approximation, right? So that's pretty interesting. I think that's pretty cool. So you can imagine if you didn't have a calculator, and in fact I think there are some historical stories about how early mathematicians, this is one way that they would actually evaluate integrals when they didn't have a calculator and they didn't have a numerical tool like Mathematica to try to get this for you, is maybe they would just carry out 4 or 5 or 6 terms, and hopefully that gets you a close enough approximation to the integral that you're looking for. All right, so now we're really cooking with gas, and what I'd like to talk about now is what about the Taylor series in multiple variables? So previously what we looked at was we looked at a function f, which basically was a mapping from one input to one output, right? The x, or the independent variable in the previous case, was just a scalar, right? It was just a single value, right? You put it through a function and you get a single value, right? So you basically get it's a plot that, you know, is x versus f of x, right? Scalar input, scalar output, right? Now, what if we consider a function which has multiple variables, a function in multiple variables, namely it maps from Rn, or n inputs, to a scalar output. So now, the picture that goes along with the function f that we're interested in approximating is the function f, it takes in x1, x2, x3, all the way up to xn. It takes in n separate independent variables and spits out a single value for that, right? So what's interesting about this is we can now still use Taylor series approximation to come up with an approximation of this function in multiple variables. Okay, the problem is it's not the easiest thing in the world. So in fact, here I've written it out, and as you can see, it's now, instead of just a single infinite series, it's actually the product of n different infinite series, and you can see that you get this expression which it looks similar to what we had earlier, right? There's a bunch of partials in here, there's a bunch of delta of how far you are away from the expansion point, and again, maybe we should also make a point now. The expansion point is now not just a single value, right? It's actually n elements long, right? Because now it's not an expansion number, it's an expansion vector, right? This point that we're talking about is now a point in n-dimensional space, right? Not in one-dimensional space, right? So it's this ugly expression, and you could work this thing out if you'd like, but what I want to focus on is actually, for 99% of the cases that, at least that I've run into, I don't need the full Taylor series expansion. I only need the first order approximation, or possibly the second order approximation of the function. So let's talk about that real quick. So we can write this in a much nicer format if we just use more compact notation. So in other words, let's use compact vector notation. Okay, so what I want to consider now in this case is, let's consider now the independent variable. Instead of it being an independent variable right now, right, it's an independent vector, right? It's a vector of n elements. So let's look at this thing as being a a vertical vector of x1, x2, all the way down to xn, right? Okay. Similarly, the expansion point, it's not just a single point any longer. It's a vector, a same thing of n elements. Okay. So now, using this compact vector notation, what's really great about this is that I can still talk about the function f of x, right? This is the original function, but now the first order approximation of this function using Taylor series is actually very easily written down like this. It's f of a plus, now usually we'd see a partial right here, but or a derivative, but now since it's a vector value derivative, we're really talking about a gradient of f at a, and also we're going to have to transpose this to make the dimensions match, times x minus a, right? So this here is the first order approximation, right, of f expanded about point A, right? And here in this case, f of a, right, this is obviously the function evaluated at A, and then here, whoops, this is the gradient, right? Gradient f of A, right? This is the gradient of f at A, right? So in other words, remember our discussion on gradient? We had a completely separate discussion on all of these vector differential calculus operators, and the gradient was really nothing more than a vector of partial of f with respect to x1, and then partial of f with respect to x2, all the way down to partial of f with respect to xn, right? And then all of this because I want to now evaluate this at x is equal to a, right? That's what that looked like. So again, the gradient in our nomenclature was a vertical vector, so I actually need to transpose it to make a horizontal vector so I can dot product it with this, right? Which again, this is now again your delta of how far away are you from the expansion point A, except now it's in multi-dimensional space, right? So this is actually really handy because this is, let me box it maybe in a different color just so we can see it easily, right? This is actually pretty easy to write down, right? All you need to do to compute this function is evaluate the function at the expansion point and then calculate a gradient right here. And the gradient is, again, just a bunch of partial derivatives, right? Now, what's also great about this, again, like we said, that's the first order approximation of the function. What about the second order approximation? So that one is actually also not that bad. In fact, here, let me erase this. I don't even want to look at this anymore because this is just too complicated and we never really need it. So let's get rid of that. I really only need the first and the second order approximation. Maybe let's just get rid of all this junk. Okay, so now the second order approximation of f of x, it looks very similar. So again, here's almost, you can think about like the n equals 0 term, and now here's the n equals 1 term. A dot with, right? And now we need the n equals 2 term. So now we get a plus 1/2 factorial x minus a transposed times this is the Hessian, so del squared f of a times x minus a. Okay, so again, this entire thing now in blue, all of this, right, is the second order approximation of f expanded about a, right? And now in this case, the only new terminology that we need to introduce here is this term, right? This is the Hessian. Sorry, where did I write this? Whoops. Yeah, there's del squared f of a, right? This is the Hessian matrix. Okay, evaluated at the point A, okay? And again, the Hessian matrix, all this is it's basically a it's a square n by n matrix where each of the entries is basically a set of mixed second partial. So this first entry, the 1, entry, this is the partial of f with respect to x1 and then with respect to x1 again. So this is like the second partial, right, of f with respect to x1. This one is partial of f, whoops, squared here like such, with respect to x1 and then with respect to x2. And et cetera, this is partial squared f with respect to x1, partial xn, right? And similarly, going down, this is partial f with respect to x2, x1, et cetera, right? So this is really just till you get all the way out to partial squared f with respect to xn, partial xn, right? So really, the entries of this matrix, so if we call this thing h, I guess, I don't know if you want to, let's do it like this. So the ijth entry of the Hessian, L squared f of a, right? This is just partial xi, partial xj of the function f, right? That's what this thing is, right? So you can see it's a square, and furthermore, you can see it's symmetric, right? Right, because the order of these partials really don't matter when you're taking mixed partial derivatives, right? So it's a symmetric square matrix of second partials, right? So, the other thing maybe we'll quickly mention here is this notation, right? This nabla squared or this del squared f. Sometimes in other contexts, you may see mathematicians use the del squared, the nabla squared here for Laplacian of f. So just keep in mind that that's a completely separate operator, right? So maybe we'll just make a quick side note that in some cases you may see del squared f. This is the Laplacian of f, and if you remember from our discussion on vector derivatives, that was given as d squared f dx squared plus df squared dy squared plus d squared f dz squared. Right? So obviously you can see these two things are not the same thing. The Laplacian of f it's a scalar value, right? It's a scalar by adding together a bunch of double second derivatives. Whereas del squared f here, this is the Hessian matrix, right? Which is it's a square matrix, right? So they're completely separate operators. It's just unfortunate that the same notation is used for both of these, right? Oh, and I guess we should have mentioned that again, this is the whole thing. This is evaluated at x is equal to a. Right? So again, this is super powerful because this thing is again allowing us a very compact, easy way to calculate the second order approximation of a function expanded at about a using the Taylor series expansion, right? So yeah, this is incredibly powerful. So you know what I want to do? Let's look at an example actually of this. So tell you what, let's go ahead and in a second we are going to jump over to Mathematica, and let's go ahead and I'll just write down the example that I'd like to examine. So let's look at a function f of just two variables, x1 and x2. Let's make this thing e to the x1 times natural log of 1 plus x2. Okay, so here's my function. Again, just the picture that goes along with this is that here you got a function f, you give it two things, an x1 and an x2, right? There's two independent variables, and what comes out of this is a scalar number, which is f of x1, x2. Right? That's the original function. You can see the original function, it's nonlinear, it's complicated. I want to get a first order approximation of it, and I want to get a second order approximation of this function, right? So all we got to do is basically calculate the gradient of the function, add an expansion point. Oh, I probably should have written that down. What's the expansion point I want to use here? Let's use an expansion point of, shoot, I did not manage the, the board very well. Let's use an expansion point of a is equal to, how about 3/2 and 1. Okay, so at this point, I want to get a first order approximation of this function and a second order approximation of this function and see what we get, right? Okay, so let's jump over to Mathematica and calculate the gradient of this function f at this point, and also calculate the Hessian matrix of the function f at this point. All right, so here we are. Let's go ahead and first define the function that we're interested in. So I'll shift enter that. And now also just so you don't have to watch me type everything in, I've prepared some of the inputs off screen. So the next thing we want to do is we need to calculate the gradient of this function. So that's what I'm going to do right here. So again, the gradient is just the partial of the function with respect to x1 stacked on top of the partial of the function with respect to x2. So let's just go ahead and take a look at the gradient. So here's what the gradient looks like. Okay, so now to get the first order approximation, I guess maybe what we should do is let's define some other intermediate variables. Like here's the expansion point we're interested in, like we said, 3/2 and 1. And then I'm just going to make a vector which is just x1 and x2, right? That's just our generic inputs, okay? So let's just shift enter this cell, get all these inputs in. Now what we want to do is we're in a position where we can now go ahead and calculate the first order approximation of the function. So this is what it was. We wrote this up on the board. So now all I need to do is basically just implement this in Mathematica. So that's what I'm going to do. So here it is. Here's the first term. Here's the function evaluated at the expansion point. And then here's the transpose of the gradient dotted with the distance away. Okay. So yeah, let's go ahead and store that as what I'm calling f first order. So if you take a look at this, here's what the function looks like. This is the first order approximation of the function. So now what we can also do while we're at this is let's just show that this first order approximation matches the actual function at the expansion point, right? We saw that in one dimension. I expect to see this also in higher dimensions. So what we're going to do is plug in at an expansion point of, a generic, our expansion point of A1 and A2, make sure that it matches. So again, if I shift enter this, you see we get a true statement. So that does work. Okay. So now what I think would be very useful is let's go ahead and plot what does the actual function look like. So let's plot the actual function right here. Okay, so that's the original function. And then what I want to do is I'm also going to plot a green dot at the expansion point A. Okay. And then what I'm going to look at is let's plot the first order approximation of the function on top of everything. So let's plot everything together and see what we end up with. So again, let's shift enter this input, and here you go. So the orange curve, that is the original function, right? It's that complicated exponent, natural log, whatever, right? And then the green dot you see is the expansion point that we're interested in, and the green plane is actually our first order approximation. So what's awesome about this approach is look at this. The Taylor series in multiple dimensions, instead of getting us a tangent line to the curve at the expansion point, we get a tangent plane to the surface at the expansion point. So again, the same ideas that we saw in one dimension are now scaling up to 2 dimensions. This would scale up to 3 dimensions or 4 dimensions. So instead of getting a tangent plane, we would get a tangent hyperplane at these higher dimensions. But that's what we're ending up with, right? This is pretty darn cool, right? That the Taylor series is giving us a way to procedurally generate this green plane here, which nails the function at the expansion point and is tangent to it, and it's trying to stay as close as it can near that expansion point, right? Okay, so now that we've done this, let's go ahead and get the second order approximation, right? So the next thing we want to do is we're going to compute the Hessian matrix, right? So again, we talked about how the Hessian matrix, it's a square n by n matrix of mixed partial second derivatives, and that's all we're going to do. So all I need to do is basically write down the Mathematica code to build up this matrix H, right? So here is just the second partial, x1, 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 x2, x2, x1, x2, x2, right? So let's just enter all of this stuff in, and we see here's the Hessian matrix, and again, we see it is symmetrical, so that's great. We're on our way. So the next thing that since we've got the Hessian matrix, let's go ahead and now compute the second order approximation. So again, this is what we wrote on the board. So it is basically, it's the first order approximation of the function plus this term here, which has the Hessian matrix. It's and basically you're going to get our quadratic terms. You can kind of see here's an x on this side and x on this side. By the time we multiply and do the dot products and the matrix multiplies, we're going to start getting some quadratic terms. So that's all we're doing right here is I am just writing it down in Mathematica, and I'm going to call this thing f second order. So again, you shift enter this, and you see, yes, indeedy, we get a function which looks like it's quadratic in x1 and x2. Okay, so again, let's go ahead and verify that this second order approximation nails the function at the expansion point, right? So if I shift enter this, we see that yes, it is true that it touches the function exactly correctly at the expansion point. All right, so then the last thing we want to do is, just like we did earlier, let's go ahead and plot. So again, here's the exact same plot. It's the same plotting module that we did earlier, except now I'm going to plot the second order approximation instead of the first order, right? So now if I shift enter this, you see, again, this is awesome. Now instead of getting a tangent plane, we're getting this I don't know if you can call it a tangent quadratic, right? But we're getting the green surface, right, which is a quadratic approximation of the orange surface, which touches exactly correctly and nails the original function at the expansion point, right? So again, this is incredibly powerful because Taylor series is now giving us a way to procedurally generate the green surface, right? Which is a very close approximation to the actual function near the expansion point. All right, so there you go. I hope by this point we've convinced you that the Taylor series is an incredibly powerful generic tool that's, at least mathematically, it's used to approximate functions using effectively polynomials, right? That's what it's doing. It's using power series. We truncate that power series, which basically gets us a polynomial, but it gives us a systematic way to calculate that polynomial. Now, what's interesting is we want to now apply this idea, and you'll see that its application across science and engineering is very wide, it's very vast. You'll see there's examples of using Taylor series to basically compute and generate numerical algorithms for optimization routines. You can also use Taylor series for linearizing dynamic systems and ordinary differential equations. So there's plenty of different ways you can use Taylor series, and it's a good tool to have in your tool chest. So with that being said, I think this is probably a good spot to leave it. I hope you enjoyed the video, and if so, I also hope you'll consider subscribing to the channel. Surprisingly, if you just scroll a little ways down, click on that subscribe button, it really does help me continue making these videos. And again, speaking of the videos, remember that a new one comes out every single Monday, so I hope I will catch you at one of these future discussions where we can all learn something new together. So until then, I think I'm going to sign off. Talk to you later. Bye.